Okay, starting the hard problems for chapter 3. So before you start any of this, again, make sure that you have installed the Rethinking package and have brought in the Rethinking package from the library function. So the hard problems are using data from a bunch of different births, and it's recording whether the baby, the newborn baby, is a boy or a girl. Boys are indicated by the number 1 and girls by the number 0. And so in order to bring this data in, this is all part of the Rethinking package. It's right here, and then I've put it into a little data frame here just for ease of looking. So we have two different sets of births. Okay. So this is one set of data. This is another set of data, and we're going to treat it all similarly. Okay. So because boys are 1 and girls are 0, if I want to know the total number of boys, then I would just sum birth 1 and birth 2, okay, which is just the name of these data sets. And it's 111. So having said that, let's get into the first two problems. So number 1 is to use grid approximation, like we've been doing already, to compute the posterior distribution for the probability of a birth being a boy. Assume a uniform prior probability, and it's asking us which parameter value maximizes the posterior probability. And this is often called the maximum a posteriori or something like that, MAP. But in other words, when we find the posterior probability distribution, we want to know which value of P of the probability of being a boy is most probable. Okay, and if that doesn't make sense, you'll see it here in a moment. All right, so this is similar to the globe tossing example that we've been using. So we'll keep a lot of the code, but change a few things. So the first thing that we'll keep is again, we're looking for a proportion, but this time instead of how much of the globe is covered in water, we're asking how much of these births are boys versus girls. Okay. So we'll use the same pgrid function, which is just 1,000 different values of P, of the proportion of the births that are boys. Okay. So we'll run that. And the question asks us to use a uniform probability distribution, but I'm going to tweak this just because I think we should. So we've all been walking around in the world for our whole lives, and we've noticed, or this is my conjecture, that about half of the people that we see are males and half are females, roughly speaking. So if I'm going to use a different prior, I'm going to use a normal distribution that is centered at a proportion of boys around 50% with some standard deviation. And so what does that look like? So I'm plotting my prior distribution here, and it looks about like this. So in other words, before I see these births, I'm saying that my most likely value is about 50%, or is 50%, but I wouldn't be real surprised if the actual value was between 40 and 60%. Okay. I think that this prior might actually be a little bit too narrow. I think a lot of people would see this and they would say, ooh, you know, they might feel more comfortable with a wider prior. The way that we would do that is to widen the standard deviation here. So I went up 1, and now you see that the prior is quite a bit wider, but I'm going to keep it at 0.05. Okay. So now finally, since just like in the globe tossing example, since we are using a binomial distribution, I'm going to use a likelihood that is also a binomial distribution, okay, and then calculate the posterior in the same way that we have been doing. And here I am looking for the number of boys, which I've calculated here. out of the number of total births, which is this code right here. Okay, so I'm going to get a posterior distribution, but the question asks us which value from the posterior distribution, which proportion of boys is the most probable. Okay, and so I'm calling that MAP, and this is the code to find that. So I go to my p-grid values, the different possible values of proportion of boys, and I look for which value is the maximum. Okay, so which index value is the maximum, right? So so when I run this, it's going to go to the value of p-grid that is the maximum, the corresponding. It's going to go to the corresponding maximum value of p-grid that corresponds to the maximum value in posterior. Sorry, that's a hard thing to say. And then I'm going to plot it, and then I'm going to put a line where the MAP value is. Okay. So when we do this, so here's our posterior distribution in black, and the maximum A posterior value is right here, and I've pulled it up right here, so it's about 0.55, right? So roughly 55% of births are boys. Okay? And then just the second question, so it wants us to sample from the posterior that we just generated, and then calculate the high posterior density intervals, the 50%, the 89%, and the 97%. Okay? So again, code that we've already used. Okay? Samples, and I'm just using the sample function. I'm sampling the values of p-grid. I'm sampling them in proportion to the values, the corresponding values of posterior. And then I just have my HDPI function where I'm looking for the intervals of the samples that I've drawn for 50%, 89%, and 97% intervals. Okay. And so for the first one, for the 50% interval, I see that it goes from 50% of the probability mass goes between, let's see, 52 and 56. Okay, so a very narrow band here. When I widen the interval to 89%, you should expect a wider interval, obviously, so the lower bound should be lower than the 50% bound, which it is, about 50%, up to about 60%. And then the 97% interval, again, should be wider still, so we're at about 47.5 and 62%.